All right, let's do a few of these real quick. So we've got calculate the molarity of this. So this is easy enough. 2.6 moles over 2.1 liters. 2.6 divided by 2.1.
The answer is about 1.2.
Two significant digits, so 1.2 moles per liter. Calculate the molarity of this. We have 0.75 moles. And again, we want moles per liter, but we have 225 milliliters. So that means we need to change the milliliters to liters. 0.75 divided by 225 times 1,000.
It's about 3.3333.
0.75 only has two significant digits, so our final answer can only have two significant digits. You could also write this as 3.3 molar. Keep in mind in this class, significant digits and units are worth points on quizzes and stuff. You have to have those things. I don't know how Mr. Heron or how Mr. Woods did it, but in this class, yes, you must have those things. They're worth points. If all you know is the units, you can still get points if you don't know how to solve it for it, okay? So if you can sit there and say, I know I need these units, put that down then. Yeah. Yep, and the right number of points or units. If this question were worth 10, 6 points would be the 3.3. 2 points would, like if you had 3.32, you would still get those 6 points. 2 points would be for correct significant digits and 2 points for the unit. 40%? Yep. A chemist prepares a 4-liter aqueous solution with 36 grams of calcium nitrate. They give us the molar mass of calcium nitrate there. That was nice of them. What is the molarity? Again, we're looking for two things. So we have 4 liters on bottom, gives us liters. 36 grams on top. Every 164 grams is 1 mole. 36 divided by 4 divided by 164.1.
The answer is about 0.05484.
Two significant digits with that 4.0. So 0.055 moles per liter. You dissolve 10 grams of manganese chloride in enough water to make 100 milliliters of aqueous solution. Every 1,000 milliliters is 1 liter. And every 125.8 grams is 1 mole. Oh, I did that wrong. Every 1 mole is 125.8 grams. 10 divided by 100 times 1,000 divided by 125.8.
That would be about 0.7949.
3 significant digits, 0.795 moles per liter. All right. Apparently I didn't give you any of the other type of problem. So you'll probably want to continue that practice here with 5, 6, and 7, and 8. I'll go ahead and do 8 with you right now so we can remember how you would do this. Oh, you can't do 8 yet. I would do 7 with you right now so that you can check how to do this to make sure you know. You wish to prepare 50 milliliters of 0.5 molar potassium carbonate. How many grams must you use? So we want to know grams. Again, this is 1 unit. So we must start with 1 unit. 50 or 0.5? Which one of those has 1 unit? 50 or 0.5? 50 has 1 unit. It's milliliters. We need to change from milliliters to liters, liters to moles, moles to grams. Every 1,000 milliliters, 1 liter. Every 1 liter is 0.500 moles. And every 1 mole is so many grams, 138.2. Give it to us. That's nice. 50 divided by 1,000 times 0.5 times 138.2. So to make this solution, I need to measure out 3.54 45 gram, actually 46 grams of K2CO3. So what that will look like is that will look just like table salt, right? A lot of them look the same. Some of them look cooler than others. Maybe I'll show you some later or something like that. But that will look like a powder. I would have to measure out 3.46 grams on a scale of this powder. It would look just like if you had a pile of table salt or something like that on, the table. I would then take this and I would put it into water, and I would slowly add water until all of it dissolves. And then the final volume I would want to get up to would be 50 milliliters of water of a solution. So I would carefully add the water until all of it dissolved, and I had 50 milliliters left over. That tells me that concentration. How many of you have ever made Kool-Aid? So what? Yeah, right? How much should you use? You have already the one with sugar in it, don't you? You have the one with sugar in it already mixed. Mr. Fancy. How about you? When I was a kid. Oh yeah, I need it. Right? When I was a kid, it was kind of sad. I had to walk pretty far to get to the bus stop. So I would actually open for breakfast. I would open a Kool-Aid packet and dump like a few things of sugar in there and mix it all around and eat that on my way up to the bus stop, like like a stick. Yeah. I was about 5 or 6 years old, and basically like my parents like weren't up whenever I was, so they didn't make me breakfast. So I would eat a packet of Kool-Aid on the way to the bus. So if we take a look at Kool-Aid, super sour Cool Cubes. Oh yeah. What is this? Mix 2 envelopes of Kool-Aid with 1/3 cup of sugar and 3/4 cups of water. Huh? That doesn't seem like enough sugar. Pour into ice cube trays, freeze until firm. Yeah, it's super cool. Super sour Cool Cubes. You don't know if you needed the Kool-Aid points. Take a look here. 1 cup of sugar, more or less the taste. Leo said he does it to the bottom is gritty, right? He does it to the bottom is gritty. Do not store in a metal container. I wonder why that is. Something tells me chemistry is involved. How about you? That sounds suspicious. My brother used to add more sugar to hot watered Kool-Aid because he thought it would make it sweeter, right? But if we saw this right here, we know it'll dissolve faster. But if we saw this, if he tried to add more at a higher temperature and then it cooled down, we said that some would come out as precipitate on the bottom, right? So what he ended up with is it's like a layer of sugar at the bottom. But it would be dissolved when it was warm. He didn't do very well in science, my brother. But yeah, that's like, he would actually, he basically did exactly this lesson, or I should say the opposite of it, right? Yeah, right. Like he didn't understand this concept, but it was a perfect demonstration of this lesson, right? Start with hot water. That way more will dissolve. The problem is who wants to drink hot Kool-Aid? Right? So as you cool it down, all of that sugar is going to come out of solution that shouldn't be there. It's very difficult. Certain things can make supersaturated solutions, but they're not the easiest thing to make. All right, so let's do the thing that we need to do today. Huh? The super sour cubes. So you're either gonna like this or not. The cool thing is we actually have a set formula, but you can do this this way as well. This is one of the few times I use the formula. I actually call this M1V1 times M1V1 equals M2V2, but you may see it in notes and stuff like that as MS. The S stands for stock solution, and the D stands for dilution. If you dilute something, what does that mean you're adding to it?
Water.
Well, if it's aqueous solution, it would be water, but as Leo said, it's a solvent, right? You're adding more solvent. For an aqueous solution, yes, you definitely would be using water. So the most concentrated acid that we have that's used regularly by us is 12 molar HCl. Why do you think we buy 12 molar HCl if we only use 1 molar HCl most of the time? Why don't we just buy 1 molar HCl? Yeah, it's cheaper. Why is it cheaper to buy the 12 molar, the concentrated stuff?
Is it because it's less quantity? Because volume?
Less volume, maybe. What does that mean? Well, there's actually more stuff in it than a bottle of 1 molar. Right? But why would it be cheaper? Let's do this. Let's maybe we're using the chemical is making you not be able to think clearly. Maybe it's clouding it a little bit. Let's think about it this way. How many of you have ever done laundry? Okay, there we go. Or we could just use the Kool-Aid. But if you've ever done laundry, does anybody have the powder? You have like the scoop and the powder. That's the cheapest laundry detergent. It's the scoop and powder. Yep. Nope. If you get the liquid one, how do you know how much to put in it? Because the powder one comes with a scoop. Yeah, right. The measuring thing in the lid tells you how much to use, right? How do they know how much to use? They make it. They should know. What's the most expensive one? The pods or the balls, right? But they're not edible. Those are the expensive ones. So why would the dry powder be the cheapest? So basically if you don't know how to measure this cost-wise, usually you buy a box of the powder and it says you can do 200 loads. And it'll be the same price as the liquid, which will only do 120 loads. And then the pods, which will only do 60 loads. They'll all be about the same price that way. But why is the powder one, you get so many more loads? Why is it in effect cheaper? Why is it cheaper for me to buy this versus buying a bottle of Kool-Aid already made? I have to pay for their stuff. So water, they're using their water, and we all know how expensive water is. The container it comes in. I know it. We're going to before we leave, though. Anybody at home ideas? There's sugar. Because they're forgetting one big thing. No, it does take time, but that's not it.
Packaging?
Country time?
Is that it? Yeah. What's your name again? Noah. Noah Montgomery? Yeah, Noah Montgomery has it in here. Noah said it's the shipment. How many of these little things these are like $1 maybe. How many of these little things can you ship in a big truck versus big old, like jugs of Kool-Aid?
A lot more.
A lot more. So imagine this, if we mainly use 1 molar HCl, but we buy 12 molar, that 12 molar can make 12 times amount of the 1 molar. So we don't have to buy for shipment, we don't have to store 12 big of things, we can store 1, and then we can dilute it, right? They're the same size, yep, they're the same size. Yep. And basically everything comes in a jug like this. So this is a jug that I've made of 1 molar, as you can see. Let me put it on here. 1 molar, as you can see. This is actually from an old jug that was filled with 12 molar. Oh, that's a good question. Anybody have the answer? This is probably a student of the month question. Why does it only go to 12 molar HCl? Very close. So Leo said he's very close. He's almost got a complete concept. He said it depends on how much water can fit in the jug. You got it. It's this right here. This right here, right? Why is it only 12 molar? Well, what's the temperature in this room? 25, 22 degrees Celsius. Go up to HCl. That means we can only get about 72 grams per 100 grams of water. So it's one of the highest concentrations that can sit at room temperature. And we might actually next week, we might change that 72 grams per 100 grams of water. We can change that from moles to liters, can't we? Yeah, right? We'll be able to do that next week. Yeah. Problem is it pressurize it, but yeah, they can pressurize it, but then when as soon as I open it, yeah, right? Yeah. Yeah. How expensive is a jug of that? Probably 40, 50 bucks. No, you would want to go get lye from the hardware store, but that quantity of lye, you would look a little suspicious. Make sure it's not the hardware store where you bought your chains and your, your binding rope. Claudia's got something planned here. Let me get through this and then entertain it. Yeah. All right, so let's take a look at using this formula. So the chemist mentioned an example 2. I don't know why they want to bring back the chemist from example 2, but we're doing it, which is to prepare 500 milliliters of a 6 molar aqueous solution of ammonia. She wants to use some 15 molar aqueous ammonia she has on hand. So that right there, the higher molarity is our stock solution. How should she prepare it? So this will be our M1. The molarity we want, the lower molarity will be our M2, or the molarity of the dilution. Words like of, that's a connecting word. That connects this molarity with this volume. So that is V2. That's the volume of stuff I want. That's the molarity of stuff I want. This is what I have. So if M1 V1 equals M2 V2, this is the most common type of molarity problem. You know what you have on hand. You know what you want. You know how much you want. So what are we figuring out here? Well, it's like Claudia said earlier. It's the cap. We're figuring out the cap. They made it. They should know, right? Isn't that what you said? So we're figuring out where to put the line on the cap. How much to start with of our stock solution, right? So we're actually calculating the cap out. So you can write all this in here. It doesn't matter what volume unit you have. You don't have to change that to liters because the molarities are going to cancel out. And we're fine with the volume of milliliters at the end. We only have to change it when we do molarity because it has to be moles per liter. We're not solving for molarity here, so we're fine with this volume. 6 times 500 divided by 15.
It's 200.
So I will start with 200 milliliters of the 15 molar stuff. That's the cap. That's how much, like, if you don't know what I'm talking about the cap for the laundry detergent. That's how much that cap that for this particular thing would be. We would need a cap the size of 200 milliliters of the 15 molar. Now, how would I finish making it once I have that?
Add 300 milliliters of the solvent, or in this case, water.
Who is that, Akshay?
Yeah.
It says we add 300 milliliters of the solvent. Is that the best way to say it, Akshay, or is there a better way to say it?
Wait, never mind. Mix just enough water to make 500 milliliters.
He changed it. Does it sound better that way? Add enough water to go from the 200 milliliters up to the 500 milliliters, right? Why is it best to say it that way, Akshay?
Well, because you're taking milliliters of a solution, milliliters of like water. It's two different things, really.
Right. Sometimes 50 plus 50 doesn't equal 100. Right? You got it. For example, if I take 50 milliliters of water and mix it with 50 milliliters of alcohol, do you think I'll have 100 milliliters of solution? Not necessarily.
No.
So that's why we're wording this. In everybody's mind, what are you talking about? You just need 500. Just add 300 to it. Come on now. Don't be stupid, right? No. We add enough to this 200 to make it 500. In our minds, that is 300, but that's not always the case. So just make sure you're careful on your wording there. That's it. That is how you do those. It's just like P1 V1 equals P2 V2. Oh, example 2 and 3. Our busy chemist of example 2 or 3 also wants to prepare 500 milliliters of 3 molar solution with 18 molar solution. So some of you will get so good at these, you'll sit there and go, oh, so this times this divided by this? Yeah. Not there yet? 500 times 3 divided by 18?
It's about 83.3.
So we'll take 83.3 milliliters, and what will we do? We'll add enough to get what? 500. Add enough water to get up to 500. I know you guys are busy today with that stuff. I think you should try a few of these problems because watching me play basketball does not make you better at basketball. Watching me do chemistry problems does not make you better at chemistry problems. Try it yourself. Have your own downfalls. You know how many chemistry problems I probably have had to do in my life? I have no clue. It would be too hard to figure out. So the only reason I look this good is because, you know, I'm like, what? The Charles Barkley of chemistry. As Jackson is to chemistry as Barkley is to basketball. Maybe not. Any questions at home? If not, I want to show these guys the laboratory because they have to do it tomorrow in front of you guys. So I'm going to let you guys go real quick. And I'm going to get that because we're